All right. Good afternoon, everyone. So, let's see, where are we at? Today's February 8th, 8th day of class, and we're finally going to start something new. So we finished up section 1.9 last time. Actually, there's one more thing I want to say about section 1.9 before we move on. The class is going to go through a bit of a transition now. So we're going to move from Chapter 1, which was mostly just, review. And now we're going to move into some ideas that you might not have seen before in other classes. Okay, so we're going to start introducing the notions of instantaneous rate of change and derivatives. Okay, which is basically what we're going to be studying for the next two chapters. So chapter 2, we're going to learn about rates of change and derivatives and these sorts of things. And then chapter 3, we're going to learn some fancy ways of computing derivatives. So that's basically where we're going. But a couple of reminders before we start. Homework 1.6 through 1.9 is due today. It's 26 questions long, so if you haven't started it, probably want to start immediately after class. And that's going to be due tonight. If you have questions on any of that homework, I have office hours today from 3 to 4:30. So right after class, I'm going to go straight home, get on Microsoft Teams. If you have homework questions or ones that you can't figure out how to do, just pop into office hours and we'll chat and work on your homework together. Okay, also don't forget about the SI sessions. There was one last night, and then there will be 2 more Wednesday and Thursday. There's also going to be a quiz today at the end of class. So for the last 15 minutes of class, we're going to take a quiz. I wasn't able to print the quizzes today, so we're going to do them on a scrap sheet of paper. I'm going to project the quiz onto the screen so you can see it. So sorry about that. Any administrative questions before we start class? If that's what the calendar says, let's check it. Let's double check. Is the quiz still planned for next Thursday? I don't even know. My life is a mess right now. All right, Blackboard. Let's log in. Let's check our schedule here. You're like light years ahead of me in terms of planning. Okay, let's see. Exam 1 looks like it's going to be on February 17th. So that would be a week from Thursday, correct. So I know I'm 2 days behind. We're going to keep the exam where it is, just because I don't want anyone getting confused about which day is going to be the exam. So we're going to keep the exam where it is, and it'll cover whatever we learn up until the end of class on this Thursday. Okay, so a week from today, we'll have a review session in class where you guys can ask me any questions that you want over any of the material, and I'll also bring some stuff for us to work on if nobody has questions. And then on next Thursday, we'll have the exam. It'll just be here in class, during class, so you'll show up, I'll hand out the papers, you'll do the exam, and then I'll grade them. Any questions about that? Yeah, Brenda?
So is there a third exam excluding the final, or is the final the third exam?
No, we're going to do 2 exams and a final. So each exam is worth, I don't even know, how much is it worth? Each exam is worth 15% of your grade, and then the final exam is cumulative. It'll be worth 25% of your grade. Any other questions? Yeah. Yeah, I said I was going to post a practice exam, didn't I? So okay, I'll post a practice exam. Was that your question too? Oh, go ahead.
I was going to ask, like, how many questions are usually going to be on the exam?
It'll be an amount of questions which you can probably answer in the amount of time. So I don't know. It really depends on the type of questions I put, because some of them are quicker than others. But I'm usually fairly generous with the time. I rarely have students run out of time on the exam. Sometimes I'll have students work up until the end, but it's not usually because they like couldn't complete the stuff in time. It's because they were like trying to rack their brain for something that they didn't know how to do. So yeah, the goal of the exam is not to make you run out of time. Yeah.
I don't know if you answered this already or not, but like, what is the format of the exam? Is it multiple choice?
No, it'll be short answer. So, you know, the questions on the exam will look a lot like the questions on your quizzes. Okay? So that's the kind of vibe that it'll be going for, except it'll be somewhat longer. You know, it'll take you the whole class period to do. Any more questions? All right, so that's a week from Thursday. So you got basically a week and a half to get ready for that. I'll talk more about the exam next class, maybe. Okay. Any other final questions before we start for today? All right. If not, then let's start. So I wanted to quickly wrap up something that I didn't have time to talk about last time in Chapter 1 notes, okay? And then we're going to start Chapter 2. So in the Chapter 1 notes, we were discussing at the very end of class last time quadratics and polynomials and how to recognize them, and power functions as well. So let me quickly recap. So power functions were, of course, functions of the form some number times x to some other number, okay? So if we can write the function like that, then it's called a power function. Okay, and then we had some more specific ones called quadratics and polynomials. So quadratics were functions of the form ax squared plus bx plus c, where a, b, and c were numbers. And we needed to make sure that a wasn't 0, because otherwise it wouldn't be quadratic, it would just be linear. Okay, so that was quadratics. And then polynomials were just these sums of power functions with non-negative integer exponents. Okay, sums of power functions with non-negative integer exponents. That was how we identified polynomials. Okay, and identifying polynomials will be important later when we talk about derivatives, because polynomials are always differentiable, i.e. we can take their derivative. So it's going to be nice if you can take a glance at a function and be able to tell if it's a polynomial or not. Okay, and the last thing I wanted to quickly touch on was the quadratic formula, which the quadratic formula and solving quadratics is the purview of another class. So I have to assume some things in this class. So I'm going to assume that you know how to solve quadratics. And if you need some review on that, then please come to office hours, okay? But really quickly, if ax squared plus bx plus c is equal to 0, then we want to know what are the x values which solve this equation. And there are the x values. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So you might have learned a song for that when you were in, like, I don't know, a grade that comes before this one. Okay, so that's how we solve quadratics. You can also solve them using factoring, of course. You just come up with a number which sums to the middle one and multiplies to the last number, and that's how you factor. Then you can just take those two things and set them equal to 0. Okay, so if that doesn't sound familiar to you, please come to office hours. Any final questions or comments before we close Chapter 1? Yep.
What was vertex form again?
Vertex form. Yeah, so vertex form is like, what is it? X minus a squared plus b or something like that. So this is a quadratic with center vertex is at a comma b, I believe. Yeah. We good with that? That's vertex form. So that's this guy. Circle that for the people at home. All right. Then we're going to transition into chapter 2 now. So these notes can be found, of course, on Blackboard. And we're going to learn something new today. Okay, we're going to learn about instantaneous rates of change. Okay, so what we need to remember, in order to compute instantaneous rates of change is something from section 1.3 called average rate of change. So let me just recall that really quickly. The idea was if we had a function, if we had a function f, then the average rate of change of f from a to b, we would take an a value and a b value, which are x values, and we would check what is the average rate of change between these 2 points. And the average rate of change was defined to be the slope of the line which passes through the points a comma f of a and b comma f of b. Okay? So if we took the slope of this line, the slope of the direct path that goes through those 2 points was what we called the average rate of change of f on the interval from a to b, okay? Or from x equals a to x equals b. All these different ways in which we can write that down, okay? So that was the average rate of change. So let's do a quick practice to remind ourselves how we do that. So if I want to do this, well, all I need to do is find the slope of a line which passes through these 2 points, right? So all I have to do for that is take the 2 points. We call one of them y2 and x2, and one of them x1 and y1, right? And all we need to do is take the rise over the run, right? So the rise would be the difference in heights, okay? So that would be f of b minus f of a. So that's the rise. And the run is the difference in the x values, right? So in this case, it would be b minus a. Okay, it would be b minus a. Okay, so that's how we write down the formula. So let's do a quick practice. So if we want to do the average rate of change of this function between x equals 2 and x equals 3, we don't even really need to draw a picture, but I'm going to draw one just for fun. So what does x cubed look like? Well, remember on the right-hand side it's going to look kind of like a parabola. But on the left-hand side, since we take a negative number and cube it, we get another negative number. It goes down like that. Okay, so this is our function, and we're going between 2 and 3. Okay, so here's 2, and here's 3. So average rate of change is going to be equal to f of b minus f of a all divided by b minus a. And who can tell me what is b and what is a in this particular problem? Yeah, b is going to be 3, or it doesn't really matter which one you choose to be b. But b can be the one on the right-hand side, so we'll pick 3. So this is the point 3 comma something, and then this is the point 2 comma something, right? So we know that a is equal to 2 and b is equal to 3. How about f of a? How do I find out what f of a is? Yeah, I plug in a into f, right? So I see f of 2, so that means wherever I see an x, I'm going to put 2. Okay, so I get 2 cubed, which is 8. And likewise, f of b is going to be f of 3, is going to be 3 cubed, which is 27. Okay, so I now know that these are the points 2 comma 8 and 3 comma 27. So if I want to find the average rate of change of f of x between these 2 points, then it's as simple as plugging in I know f of b is 27, so I'm going to put that in where I see f of b. And I know f of a is 8, and I know b is 3, and I know a is 2. So 27 minus 8, I think, is 19 over 1, which is just 19. Okay, so physically, well, not physically, but I don't know, metaphysically, what that represents is the slope of this line which passes through those 2 points. Okay. So, average rate of change is a very important concept which we are going to use to formulate instantaneous rate of change very soon. So, before we move on to a more complicated topic, are there any questions on what is average rate of change, how do I find average rate of change, and what does average rate of change mean geometrically? Okay, let me see some thumbs. How do we feel about average rate of change? Thumbs up if you like it, thumbs down if you're not so thrilled about it. Okay, it's looking pretty good out there. If you are still confused about it, just make sure you follow up with me in office hours. Okay, so I guess we'll just continue on reading. This is a bit of a different style of note for the first 2 sections of this chapter for some reason. So okay, let's read. Suppose we wanted to find the slope of a function at a specific point, x equals a. So rather than saying, well, the slope of the function on average between these 2 points is 19, what if I wanted to know what is the actual slope of the function at a exact point, a, okay, instead of between 2 points at x equals a and x equals b. So what if we wanted to find the slope of f of x equals x cubed at x equals 2, rather than between x equals 2 and x equals 3? Okay, so this is the way that we're going. Okay, this is the way that we're going. So the first problem, well, is really just an exercise to show you why we can't really just use the average rate of change formula. So the first step is to try, well, let's try just finding the slope by applying the average rate of change formula where we take a and b to be the same. Okay, so I'm just going to take, well, the average rate of change formula tells me the slope of this line, so if I put b on top of a, then maybe that'll get me what I want. So let's do that. If a equals 2 and b equals 2, well, when we plug in f of a, we're going to again get 8, and this time when we plug in f of b, we're going to get 8. And if I try to plug that in for my average rate of change, what am I going to get? 8 minus 8 over 2 minus 2 equals 0 divided by 0. Are we happy with that? Why are we not happy with that? Well, 0 divided by 0 is actually undefined, right? We don't know what it is. In fact, there are circumstances where 0 divided by 0 could be infinity, it could be 17, or it could be negative infinity even. Okay, we don't actually know. So we have to do something a little smarter than that. Okay, and okay, so let's answer the question. Why does the calculation you performed in part 3 not work? Well, 0 divided by 0 is undefined. Right? We can't divide anything by 0. Okay. So now we're going to do a different step. Okay? We're going to do something a little bit different. We're going to try computing the average rate of change of f of x between x equals 2 and 3, between x equals 2 and 2.1, and x equals 2 and 2.01, and 2 and 2.001. Okay, so let me draw a quick picture of what this looks like for each one. So the first one, we take 2 and, let me just copy this down to each one. Okay, and what we're going to do is something a little clever. We're going to take points which are closer and closer. Okay, so first we take the slope of this line, and then we're going to move. Okay, if my iPad will move screen. Then we're going to move the point much closer. We're going to do 2.1. And we're going to take the average rate of change between those 2 points. Okay, and then we're going to move it even closer. Right, 2.01. And take the average rate of change between these two. Okay, and so on and so forth. So that's going to be our clever idea. So if we do it for this one, we already solved. We got 19, I think. For the second one, well, it's going to be 2 cubed, so 8 minus 2.1 cubed. Not 8, sorry. We'll do the other way around. 2.1 cubed minus, so this is our B, this is our A, minus 8 all over 2.1 minus 2. So if we plug that in on our calculator, which is a good thing I brought one today, we get 1.261 divided by 0.1, which is 12.61. Okay, and now we're going to do it with something which is even closer. Okay, so we're going to take 2.01. So 2.01 cubed minus 2 cubed over 2.01 minus 2. We get 0.01 on the bottom, and on the top, we get 0.120601, which comes out to 12.0601. Okay, and lastly, we're going to, these 2 points are practically on top of one another at this point. It's hard to even draw them. Okay, so 2 and 2.001. This was 2.01. So now we do 2.001 cubed minus 2 cubed, all divided by 2.001 minus 2, which is, our denominator will be 0.001, and our numerator, is that right? No. 2.001 cubed is 8 point, what am I doing? Minus 8. We get 0.012006001. So this is actually equal to 12.006001. And we look for a pattern, right? First we computed it between 2 and 3 and we got 19. Then we computed it between 2 and 2.1, we got 12.61. Then we did it on an even finer interval, we got 12.0601. And then on a smaller interval still, we get 12.006001. So what is the pattern here? What is this number getting close to? Yeah, it's getting really close to 12. You can imagine that if the pattern here is that we keep adding a 0 after the 12 but before the 6, and add a 0 between the 6 and the 1. If you keep doing that, then you're just going to keep going on and on and on, and you get like, 12.0000006000001, right? And these numbers are getting closer and closer to the number 12, right? So our guess is the slope at x equals 2 is 12. Okay? Any questions about this process? Okay, let me do a quick little drawing here just to make this a little bit more clear what's happening. So I'm going to do this nice and big. So say we have a nice curvy function like this. So we want to know what is the slope at A. So what we do is first we take a point which is further away, call it B1, right? and we take the average rate of change between those 2 points. And then we take a point which is closer, B2 maybe. And we take the average rate of change between these 2 points. And then we take a point which is closer still, B3, right? And we take the average rate of change between these 2 points, right? And the thought here, okay, is that if we look at the slope of each of these lines, the slopes of each line are actually getting closer and closer to the slope of a line which comes in and just barely touches our function at that one single point and then goes straight on. Okay? So we take the limit of the average slopes, right? The average rates of change, as we move the second point closer and closer and closer and closer to the point at which we want to know the slope. And this is how we define the slope of a function at a point, okay? So before, when we talked about slope, the only thing we could describe was what is the slope of a line. But now we've come up with a way in which we can describe what is the slope of something curvy. And the trick here is we have to talk about where we're just expressing the slope, okay? Because the slope here is going to be different than the slope up here, right? Because this part's rising faster than this part down here. Okay, so this is how we define the slope at a point. So we have average rate of change, which goes from one point to another on the function, and then we have the limit of this tells us what we call the instantaneous rate of change, or the slope of the function at a point. Okay? So we went from slope of a function between 2 points to slope of a function at a point. Are there any questions about this process so far? Okay, if not, then let's, yeah, go ahead.
So if you're finding the slope of a point, is that pretty much like, if that point was part of like a linear ordeal? Like, I just don't, I'm confused how you're starting from a point that's far away and then you're just getting smaller, 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 and then somehow you're just like, all right, well, it's 12.
Right. So here's what I want to do. Ultimately, I want to know what is the slope of the brown line, okay? But what I tried doing was plugging into average rate of change. And when I did that, I got 0 over 0, which obviously is not the slope of this line. We can tell the slope of this line is some positive number, right? So what we did instead was, well, I don't know what the slope of this line is, but I can easily find out what is the slope of the blue line and the green line and the purple line, okay? And I can tell that the slope of the blue line is somewhat bigger than the slope of the brown line, right? But the slope of the green line is a little bit closer, and the slope of the purple line is closer still. And if I just take this process and keep repeating it with closer and closer and closer points, then the slopes of these lines are going to become very, very close to the slope of this line. So for our example, we had, I think, like 19, 12.61, and then the slope of the purple line was 12.0601, right? And we just kept doing this, and we noticed that the slopes of these lines were gradually getting closer and closer to the number 12, which is why we say, the slope of the brown line must be 12. Does that answer your question?
Yes.
Okay.
Why don't we just start with a really close point?
Oh, sure, you can start with a really close point, but it's easier to see the pattern you can start with a really close point, but if you start with, say, 12.0601, right, you still need to have intermediate points in order to be able to say that this sequence of numbers is getting really close. Because how do you know the next number won't be 11 or 9 or something like that? Maybe it just keeps going down, 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 down. So depending on the function, yes, you can start closer to get a slope which is ultimately closer to the final slope. But you still need this process in order to be able to see that this sequence of numbers going from 19 to 12.61 to 12.0601 to 12.006001, we can see that these numbers as a sequence are marching steadily closer to 12. If I just start at 12.006001, I can't say definitively that the slope of the function at that point is going to be 12 without further guessing something like 12.0000600001. So, basically you need to do the average rate of change a few times either way. So it's just a matter of preference in terms of where you start, I guess. Any other questions? These are great questions, by the way. Yeah, Emily.
How would we go about proving that without a calculator?
Well, okay, yeah. So, I mean, yeah, I'm not going to ask you to do something like this without a calculator, is what I'll say. I would either allow you to use a calculator for this type of calculation, like for your homework, feel free to use one. But I'm not going to allow calculators probably for the exam just because there's too many ones that you can program to solve things for you. So, and then it just becomes an issue of policing who has what calculator, and I don't want to make students go buy a special calculator just for my class. It's just a mess. So you can use your calculator on the homework, but this is just to demonstrate a point. Okay, I'm going to move on now. So what we're supposed to do next, okay, according to these notes is, okay, based on our observations, we're supposed to come up with a method for computing the slope of a function y equals f of t at a point x equals a. And the method that we've basically discovered is, well, take average rate of change of f of t on smaller and smaller intervals with a as an endpoint. So the sequence of intervals could go something like a comma a plus 1, a comma a plus 0.1, a comma a plus 0.01, dot dot dot. Or we could keep a on the right hand side and do a minus 1 to a, and then a minus 0.1 to a, and then a minus 0.01 to a. Okay? Doesn't matter if you start on the left or start on the right, but a should be consistently one of the endpoints. Okay, so what do? We take the average rate of change on smaller and smaller intervals with a as an endpoint, and do what? And look for a pattern in the numbers. E.g., what we want to do really is guess what we call the limit. Okay, so the limit is the number which all of these guys are getting close to. Okay, so for this example, the limit was 12. Okay, because those numbers were getting closer and closer to 12. Yes?
So will x approach 12 basically to infinity but never pass it for a limit?
It depends on your function. For this function, then yes, it's going to slowly get closer and closer to 12 but never touch it. Because if you take a point which is a little further away, no matter how far away it is, it's still some distance away, which is why you'll have some difference between the average rate of change and the instantaneous rate of change. It just might be like, 100 billion zeros, in between your 12 and your 6, right?
So does that mean that there's always a relative amount of uncertainty between numbers? If it never really touches or never really coincides with that number?
Well, okay. I mean, in this particular example, you know, okay, this is the problem with teaching limits in this way, because I'm very sort of carefully dancing around an actually elaborate mathematical concept called taking a limit, right? And what I'm saying is, well, just plug in average rates of change over smaller intervals and check if the number's getting close to something. And that's a very imprecise way of saying it, right? And we have a super precise way of actually defining what this limit means, but we don't teach it in this class, just because it tends to be a little bit higher level of mathematical thinking and very different from what a lot of students have seen before. So we don't teach it in the business version of this class. But if you want to see definitions of real limits, well, you can come to my office hours, or you can take 141. But yeah, so, you know, who's to say that this number isn't actually approaching 11.99, right? Yes, you're right, there is a relative amount of uncertainty, but the examples which I'll give will be fairly obvious if you have to do it on like your homework or on a quiz or something like that. Is that fair? Okay, I'm gonna move on. So this process, okay, is how we find what we call the slope of the function at a point, okay? Another way of saying that is saying the instantaneous rate of change of f at a, okay? That's the same thing as the slope of f at a, okay? Same thing as slope of f at a. Okay, it's also called the rate of change of f at a, okay? And we define it, okay? We define it to be the average rate of change of f as the interval around a gets shorter and shorter. Okay, so that's the process which we just defined. Okay. So we just found the slope of f of x equals x cubed at x equals 2, for example, or also the instantaneous rate of change of f at x equals 2. Okay. All right, and the real fancy math word that we use for this thing, okay, is called the derivative. Okay, so we write it down as f. We write this down, the way we say this is f prime of a. That's how we say it, okay? And we define the derivative of f at a to be the instantaneous rate of change of the function at that point, okay? So for our previous problem, we had f of x equals x cubed. We found the slope of that function at 2. The way we write that in terms of our derivative notation is like this, f prime of 2, okay? This means the derivative of the function at the point x equals 2, the instantaneous rate of change of the function at x equals 2, the slope of the function at x equals 2, and all of these sorts of things, okay? So what we're really doing here is describing sort of, okay, if you were driving on this kind of roller coaster of a road, then the derivative is going to express the pitch, basically, which direction you're facing, kind of, in terms of how steep the function is at a given location, right? So for lines, it's always the same steepness the whole way through, right? But for a curvy function, the steepness of your hills is going to change. Sometimes you're going uphill, sometimes you're going downhill. Sometimes it's really steep, sometimes it's more gradual, right? So this is what we call a local property. So what we do is we just take a look at this function, and let me pause it somewhere here. Okay, so this, oops, shouldn't have done that. Okay, so let's see here. How about there? Okay, so if we take a look at this line here, it sort of describes the direction that the function is going at the point where the x value is like negative 5 point something, right? You can see the x value there is negative 5 point something, and we just take a look at, well, what is the function doing when that x value is occurring, okay? And the answer is, well, it's kind of headed in the same direction as this red line, which we call the tangent line. So we say, well, the slope of the function at that point is just whatever the slope of this red line is, okay, the tangent line. Okay, and this is how we define what it means when we say slope of something which is curvy. We say, well, we define it at each point on the function to be the slope of this line which comes through and goes in the same direction that the function is going in at that particular moment. Yeah.
So the red line is what we're trying to find, basically.
Well, really what we're interested in is what is the black line doing at a particular moment. And at this particular second, what's happening is the red line and the black curve are traveling in the same direction. So if I want to describe what direction is the black curve going at this particular moment, the way I do it is by saying, well, it's going in the same direction as this red line whose slope is this or whatever. So I want to know what is the slope of the red line so that I can describe what's happening to the black curve at that moment. So a bit of a subtle difference from, I think, what you were saying. Any other questions?
So would you determine whether the function is increasing or decreasing at that time by looking at the slope?
Exactly. We're going to talk about that in the next section, actually. So you're exactly right. We are going to determine whether a function is increasing or decreasing by looking at the slope of the tangent line at that point, right? Okay, very good. Okay, so let's use the graph of a function, okay, to tell whether each of the following quantities is going to be positive, negative, or 0. Okay. So let's use the graph of x squared. We don't need a graphing calculator to do it. We can just graph it. Okay, that's a parabola coming through like this. Oh, that's a pretty good parabola if I don't say so myself. Okay, so let's first geometrically try to understand what each of these things mean. Okay? First one, f prime of 1. It means we look for when the x value is 1. Okay, so here's the x value, x is equal to 1. And what we want to know is what is the slope of the function? Okay, well, what we said was the slope of the function is just the instantaneous rate of change of f at that point. Okay, so all I'm going to do is put a point here, and I know that the slope of the function at that point is defined to be the slope of this tangent line, which comes in and just barely kisses our function at one single point and moves on. So I know that f of 1 is the slope of the blue line. So what do we think in terms of f of x squared? We want to determine whether each of the following quantities is positive, negative, or 0. If f prime of 1 describes the slope of the function at 1, which is the same as the slope of this blue line, do we think it should be positive or negative or 0?
Positive.
Yeah, positive, right? Because the tangent line is going up. It has a positive slope, which means the function has a positive slope at that point. Okay, very good. How about f prime of negative 1? Do we need a picture, or can we just tell? Is it going to be positive, negative, or 0?
Negative.
Yeah, negative, right? Because if I drew in the picture, it'd be over here, and it'd be a tangent line going like this, which is going down, right? Okay, and so on and so forth. And the only other really important one here is what's happening when f to f prime at 0, do you think? Yeah, what would our tangent line look like for x equals 0? It's going to be an exactly horizontal line at y equals 0. Someone said that as well. So what is the slope of a horizontal line? It's 0, right? No rise, but lots of run. Okay, so this is the basic idea behind derivatives, okay? We want to describe what is the slope of that tangent line. Okay, I don't want to rush this because this is the first time you've seen derivatives, first time you've seen this kind of instantaneous rate of change stuff. Any lingering questions on this? I know it's a little bit much to take in for the first time.
So, like, we talked, what is the difference between, like, instantaneous rate of change and average rate of change? We talked about both, and it sounds like the same thing.
Can anybody answer his question? What is the difference between average rate of change and instantaneous rate of change? Yeah?
Instantaneous rate of change does the same thing, whereas average rate of change is
So when we're doing the average one, we just take a bunch of instantaneous ones.
Not quite. So what Alyssa, right? What Alyssa was saying was that the average rate of change, okay, is between 2 points. So I take a point A and I take a point B, and what I do is I draw this funny line which passes through both of those 2 points. So I have 2 points which is on the function, and I draw a line between them. Now the slope of this line doesn't really describe what is happening at the point A for our function. What it describes is kind of, well, what is the function generally doing in this region, right? What is the function generally doing over this interval? And the answer is, well, on average, it's basically behaving like this line, okay? So that's what average rate of change is. So it's between 2 points. When we take the limit, though, as the average rate of change, when the interval gets smaller and smaller, so first my interval goes from here to here, then my interval goes from here to here, and then my interval goes from here to here, and the interval just keeps getting smaller and smaller until it's collapsed onto itself. Then this tells us what is the slope of this tangent line, okay? So these lines which go between 2 points, we have a name for them. They're called secant lines, okay? So a secant line kind of passes through 2 points on the function. But a tangent line is special. It comes in, it just barely touches our function at 1 point, and then it goes off, okay? Barely comes in, touches our function at 1 point, and goes off, right? So the instantaneous rate of change is the slope of that tangent line, which can be expressed as the limit of the slopes of these secant lines, because the slopes of these secant lines get closer and closer and closer to the actual slope of this tangent line. Does that answer your question?
I think so.
Okay. You can stay after class and we can chat some more about it. Any other questions? Yeah, Brendan.
Could this method be used to determine the exact slope of a trend line?
The exact slope of a trend line?
Yeah.
Yeah, sure. I mean, any curve that you have, as long as it's sufficiently smooth, you can use this process to find out what is the slope. So all of these times where we had those problems talking about, well, what is the slope of the cost function, right? What's the marginal cost? We can now extend that to cost functions which aren't lines, right? We can say, what is the slope of the cost function when we're producing 300 units? And now we can say, well, if we produce another unit, the cost is going to go through the roof, so we shouldn't do it, right? So yes, we're very much going in that direction. Any other questions? And this is great. You guys are so engaged today, asking so many good questions. All right. Well, let's talk about something else, which is really just the same exact thing disguised in a different, funny way. Okay, which is instantaneous velocity. Okay, well, the instantaneous velocity of an object at a time t is defined to be the average velocity of the object Okay, the average velocity, that's just average rate of change. Okay, so this is basically instantaneous rate of change, and this is average rate of change, right? So average velocity is just the average rate of change of a distance function. As the interval containing t gets shorter and shorter. So in other words, the instantaneous velocity of an object is just going to be the instantaneous rate of change of that object's position or distance function. Okay? So let's take a look at this quick example here, and then we'll probably take the quiz. Maybe we'll do a little bit more. We'll take a look at this example first. So suppose we throw a grapefruit straight upwards into the air. So we have this function here which is describing the height of our grapefruit, right? So let's do a quick picture of what this graph looks like. Anytime you get a table like this, it's never a bad idea to do some graphing. So it starts off at 6 feet high, and then 1 second later it's like 90, and then it's 142, and then it's 162, and then it goes down to 150, then it goes down to 106, and then it goes down to 30. So what does it look like? We got a point here, we got a point at 1, 90, 1, 2, 3, 4, 5. So at 3 it's 162, so that's where it reaches basically close to the peak. And it probably looks something like this, right? Okay. Now I have a question for the class. This is our y, height, and this is our time, t. The question says that we throw the grapefruit straight upwards into the air. Now, if I throw something straight upwards into the air, then what's going to happen is it's going to go directly up, and then it's going to directly fall back down on the exact same spot that I threw it, right? Because I threw it directly upwards. So my question for the class is, why does our graph look like a curve like this? Shania?
Your independent variable isn't distance, it's time.
Exactly. So we got to be a little bit careful thinking about what this graph is telling us, okay? It's telling us the horizontal axis here is in terms of time, and the y-axis is in terms of feet above our head, okay? So even though it looks like, okay, yeah, this looks like what it would look like if we threw something in this direction, what really it's describing is actually this horizontal axis isn't describing forward and backwards distance, it's describing forwards and backwards in time, okay? So if I think about my grapefruit, here's basically how it works. So here's me throwing the grapefruit. After 1 second, what? It's at 90. After 1 second, the grapefruit is directly above my head, 90 units. After 3 seconds, it's at 162 feet, but still directly above my head. Okay, so even though this thing is going like this, really what it's describing is the path of the grapefruit going straight up and then straight down on my head. Okay, so a little bit of a difference there between these two graphs. Okay. Any questions on this, on what this graph is looking like here? Okay, so let's move on and try to answer the question. So it says, why is it impossible to exactly determine the instantaneous velocity of the grapefruit at t equals 1 at t equals 1 using this table. Yeah, in the back.
Because you're not given an actual function, you're just given data points, so you don't, it's not proven it's the actual exponential function.
Yeah, exactly. We're not given the function, we're just given a few data points. And the data points are relatively far apart from one another. Okay? If I wanted to do our method would be to take the average rate of change of this function on 1, 2, and then on 1, 1.1, and then on 1, 1.01, ... That's our method. But can we do this method? No, because I don't know what is f of b if b is 1.01. Okay? So I can't use my normal method. Okay? So in other words, we are missing data for f of 1.1, f of 1.01, etc. Okay? We would want to use that information. Okay. But still, we want to give a good guess. We want to give a good guess for what's the instantaneous velocity, or the average rate, the instantaneous rate of change at 1, using the information that's in the table. So does anybody have a good heuristic for which we can, what's the best we can do here? Yeah? Is your name Gino, by the way? Yeah, okay, Gino, what's up?
I would just guess, like, find the rate of change between 0 and 1, and 1 and 2, and then, like, finding like, the difference between them.
Yeah, I really like that idea. So Gino says, well, I don't actually know that this curve looks like this, okay? But what I could do is say, let's find the average rate of change between, where is it at 2 again, 142? Let's find the average rate of change, okay, on the interval to the right, and then let's take the average rate of change on the interval to the left. Okay, let's find this slope, and then let's find the slope of the average rate of change on the right. And then let's average them. Okay? So from the left, our average rate of change is 90 minus 6 over 1 minus 0. And then the average rate of change for the next interval is 142 minus 90 over 2 minus 1. So if we take those two numbers, we get, well, this one's just 84, right? And then the other one's 52. So our guess, it's the average of slopes to the right and left. That's a great guess. So we take 84 plus 52 and divide by 2. And that's our guess. Okay, any questions on this example before we start the quiz? Okay, then today I'd like everybody to please take out a scrap sheet of paper. Please borrow a scrap sheet of paper if you don't have one. And I'm going to display the quiz on the screen.